Good. All right. Jacob, what about you?
I got up to the start of titration, but I was mainly focusing on like finding the pH questions.
Good. All right. Yeah,
Yeah.
pH, PK questions, they're a bit of the bulk and they're a bit challenging. So I think it's very important you spend a lot of time on that. Sid, what about you?
I'm just about finishing inquiry question 2 after that.
Okay. Akshita, how about you?
Yeah, I got into the midst of titration and I was just watching a couple of videos on how to do it because we have stuff in school about that.
Very important. And make sure whenever you guys do your practice run for titration, you treat it like the actual exam, right? So you really practice your technique, ask as many questions as you can, because most of you will have titration as your assessment task. Some schools record you for your titration to see your actual technique. Other schools will literally have a concentration of the acid or base, and whoever gets closest to that value will get the closest mark to 100%, etc., right? And make sure you also brush up on your report writing. So accuracy, validity, reliability, and titration, and discussing that is really important for your report, but also for that final exam, because you can also get method questions, etc. Good. All right, I think all of you are doing okay in terms of your progression. Best case, you would want to have finished Mod 6, but I understand, doing titration by yourself and running through all that is very daunting. So at least I hope you all had a read of what titration is generally, okay? Good. The good thing for me now is I can run through content a little bit faster. So thanks everyone for going through things at a good speed. Let me just open up HSC Chemistry. All right, so we spoke about historical theories of acids and bases. So just very quick recap. What scientists do you really need to know, and what scientists are important additionally to know for your trial exams? So Sid, what are the main 2 scientists you need to know for HSC Chem?
Arrhenius and Bronsted Lowry.
Good. Arrhenius, Bronsted Lowry, right? And before Arrhenius, Rithania, what are some scientists who you may want to include in a long response answer that's, let's say, 6 marks?
Was it Humphrey Davy or something?
Good. Yeah. You should have an order in your head, right? So quick recap. First scientist was Lavoisier, and he proposed that acids contain oxygen. First scientist to define it by composition, but as you clearly know, he was wrong, right? And then shortly after him, there was Humphrey Davies. What did Humphrey Davies state actually about definitions of acids?
He proposed that hydrogen gas was not present in the metal.
Good. Okay, so you're explaining his observation, but what was his final conclusion? That's the high yield part. What did he say acids contain?
Hydrogen.
Good, that's it, right? So remember, Humphrey Davies has a H for hydrogen. He defined acids as containing hydrogen. He studied acid-metal reactions, right? The only con is some substances contain hydrogen, but they're not acidic. And so that takes us to Arrhenius. Now, the speed in which I went through those above scientists, that's all you need to know about them, okay? So as long as you can list them, their main definition and one flaw, you're fine for a long response question. Now we're going to Arrhenius. Arrhenius you need to understand very well. You need to know the pros, cons, definitions. So Sid, take it away. What's a definition of an acid or base according to Arrhenius? Sid, what did Arrhenius state about acids and bases?
Sorry, my mic was off.
Yep.
Yeah. So he defined acids as it dissociates hydrogen ions in solution.
Good. And what about bases?
Bases, they dissociate hydroxide ions. And
Good.
you're only considered in water, acid-base reactions in water.
Good. The only change I would make is make sure you include aqueous solution. Very small point, but aqueous dissolved in water, very important and constraining the definition in a sense, because we'll soon learn that acids and bases can behave such a way outside of water as well, right? So hydrogen ions in aqueous solution, hydroxide ions in aqueous solution. He also defined neutralization. Anyone know how he defined neutralization? It's the combination of hydrogen and hydroxide ions to form water, right? Because as you might remember, the net ionic equation for neutralization is H plus OH minus forms water, right? And so Arrhenius was the first scientist to be able to explain neutralization reactions. What were some of his other advantages, Jacob? What were some of the pros of Arrhenius theory?
He led to the development of the pH scale.
Very good, right? Because he defined an acid as containing hydrogen ions. So pH scale quantifies hydrogen ions. Very good. Nathaniel, what was another pro?
The strength of an acid is from the degree of ionization.
Very good, right? And what percentage of ionization do you need to be strong, Rithanya?
100.
100. Anything less is weak. Very good, right? Akshita, what were some cons of Arrhenius theory? We mentioned 3 pros, now we need 3 cons.
Sorry, my mic. He didn't acknowledge the fact of the solvent.
Good. Yeah. So what do you mean by that? He didn't account for the role of the solvent.
Like how the solvent it partakes in neutralization.
Yeah, good, right? So quite literally, the solvent influences whether a substance will behave as an acid or base, right? And he didn't account for that. Very good. Okay. The main thing to note is when you say he didn't account for the role of the solvent, what you're also trying to say is he only explained acid-base reactions in water, no other solvents. Make sure you mention water specifically. Or some other cons, Sid. Give me 2 other cons.
Some bases didn't contain hydroxide or dissociate hydroxide ions.
And what's an example of that?
Ammonia and hydrogen chloride.
Not hydrogen chloride. Hydrogen chloride is hydrochloric acid if it dissolves in water, right?
Isn't
So
it gaseous state?
yeah, in gaseous state, good, but that wouldn't be an example of some substances are basic, but they don't contain the hydroxide ion. So I think the way I would structure that, so the hydrogen chloride being gaseous, the reason he couldn't explain that was Akshita's point, which is he could only explain acids and bases in water, not in gaseous state, etc. Right? So that is your support for the first point, which is it didn't account for the role of the solvent, so he couldn't explain ammonia reacting with hydrogen chloride gas to form ammonium chloride. Does that make sense, Sid?
Yeah.
Good. The second point about certain substances like magnesium oxide, sodium oxide, not even containing the hydroxide ion, but being basic in solution, that's a separate point. Good. Good. And you can also explain carbonates. You couldn't explain why metal carbonates were basic. They have a carbonate ion, not a hydroxide ion, right? What was another con? Nathaniel?
Was it something about the salts not being neutral or something?
Exactly, right? You're going to learn very soon how that's the case, but certain salts like ammonium chloride are acidic, and certain salts, like we just said, sodium carbonate, it's a salt. Sodium metal carbonate, non-metal ion, are basic. And he couldn't explain that. So the pH of salts, very good. So when you've got 3 pros, 3 cons, you're set for your exams. So now we're going to go to Bronsted Lowry. I'm sure you all know the definition now because you went through it last lesson. And I'm sure you've read it. From now on forth, your definition of an acid and base is based on Bronsted-Lowry theory. All your chemical reactions are to be written in Bronsted-Lowry theory. Okay, so Bronsted-Lowry theory states acid is a proton donor, base is a proton acceptor. Jacob, why were you talking about protons all of a sudden? What is a proton?
The proton is just like the hydrogen, right? Like the hydronium ion.
Very good. Proton is just a hydrogen ion, right? Don't mix it with hydronium. A proton is just a hydrogen ion. Okay. And what will happen is the hydrogen ion by itself is unstable, as you can see in this reaction right here, right? So when an acid really releases a hydrogen ion or a proton, it's unstable, and so what it does is it will combine with a water molecule, form what's called a coordinate covalent bond, where it'll just sit and take the electrons of that oxygen in the water, right? It won't be an even sharing. As you can see in the circled electrons, both the electrons are black, aka they come from the oxygen. None of them come from the hydrogen ion because it's just a proton. And what you end up with is a special polyatomic ion that has 3 hydrogens, 1 oxygen, and has a net +1 charge because of the hydrogen ion. It's called the hydronium ion. So what I'm trying to get across here is that the hydronium ion is actually what the hydrogen ion becomes because it's unstable. So the correct way to write this reaction, so initially we wrote acids and bases reacting like this. HA becomes H plus and A minus. From now on, you are not to do that. As you can see, the main issue with Arrhenius was that he didn't account for the role of the solvent. In Bronsted-Lowry theory, we write the solvent, which is majority of the time going to be water, in the reaction. Okay, so this is an acid, and it's going to be reacting with the solvent that we can see here. Okay, and Ruthania, what did we say that an acid is? Donor or acceptor of protons?
Donor.
Good. So it's going to be donating a proton. Well, what is a proton? It's a hydrogen ion. So think of it as 1H. So that H is going to be transferring to the water, right? And that's exactly what's being shown here. The H gets transferred to water. When the H gets transferred to water, just like we said, we form this new polyatomic ion that now has 3 hydrogens, the same 1 oxygen, but since it's a proton, adds a +1 charge. This is the hydronium ion. And everything else is the same. We're left with the A minus. So this is how, from now on forth, you will write an acid dissociating or ionizing in water. And as you can appreciate, the acid here is acting as a proton donor. What is the water acting as? Actually, what is the water doing?
Is it acting like a base?
Good, right? It's behaving like a base because it's accepting a proton. A proton acceptor is a base. So what we say now is that the acid is a Bronsted-Lowry. So HA is a Bronsted-Lowry acid. H2O, since it's accepting a proton, is a Bronsted-Lowry base. Okay. And since there's been a transfer of protons, technically, what kind of reaction is this, Sid? What did Bronsted-Lowry define as a proton transfer reaction?
Neutralization.
Good. This is technically a neutralization reaction taking place. So make sure whenever you explain Bronsted-Lowry theory, explain all 3 definitions: acid, base, and neutralization. Okay, very good. Now I'm going to introduce you to 2 new terms. And it's this term of conjugate acid and conjugate base. Okay, so the first point is referring to the Bronsted-Lowry acid. When the Bronsted-Lowry acid, in this case HA, donates a proton, whatever it's left of it, Britannia, what's left of HA on the right side of the equation? What does HA become after donating a proton?
It just becomes A minus.
Good, right? So whatever's left of HA, the Bronsted-Lowry acid, is now called the conjugate base. Okay, so remember the acid becomes the conjugate base on the other side of the reaction. In the same way, I think we can all infer the Bronsted-Lowry base here, water, when it accepts a proton, what does it become? Let's go to Jacob.
The
What-
acid.
Good. What do you call it? It's a full term.
Oh, conjugate acid.
Good. Conjugate acid. Right. Now, let me ask you this. I'm sure you've all come across this in your reading time. Sid, why is this important? Why are we calling things conjugate acids and conjugate bases?
Because they have like the inverse like strength.
Very good, right? So it's very important for determining the strength of acids and whatever's left of them on the other side of the equation. Now, as you might know, not all reactions go to completion. Most reactions, as you remember in Mod 5, do not go to completion. In fact, they form an equilibrium. So I want you all to tell me what would be the dissociation equation for, let's say, acetic acid, right? So we've got CH3, COOH. Akshita, finish off the reaction. It's going to react with water, and what do we make?
A hydronium ion.
Good.
And
So take the H goes to water. So what's left? So the water has become the hydronium ion because it obtained a hydrogen. What's left, Akshita? What's this? That's what's left, right?
yeah.
That's the acid type. Very good.
Yeah.
CH3CO minus. Okay, good. So filling that all in, states included. This is your reaction. So very quickly, Sid, who's the conjugate base? Who's the conjugate acid?
So the conjugate base is the acetate ion,
Good.
and the conjugate acid is the hydronium ion.
Good. Conjugate acid is the hydronium ion. Very good. Now, let me just draw an arrow to show you the conjugates as Sid mentioned. So conjugate base, and the water will then become the conjugate acid. Now, when we're talking about strength, as you can see here, this arrow is reversible. So what is that telling you, Bethania, about the strength of acetic acid?
It's weak.
Good, right? So what we're going to write now underneath acetic acid is a weak acid. Weak acid. Okay? Now, there's a few rules in determining strength that actually make a lot of sense. They make sense kind of in an analogy way, but also I'll explain the underlying principle shortly. Okay? But the conjugate of a strong acid is a very weak base. That's so weak, it's technically neutral. Let's try understanding that, right? Imagine HA was HCl. And imagine the A minus ion is your Cl minus. Everyone with me? So look at the reaction up there. We know HCl is a strong acid because the reaction goes to completion. Everyone with me? Right? Now, we know that Cl minus, as we labeled earlier, is our conjugate base. Now, what did I tell you? The conjugate of a strong acid, what is it? What's the strength of the conjugate base?
It's a weak base.
Very weak. Not just weak, very weak, or neutral/neutral, right? How does this make sense? Well, let's think about this, right? HCl is a strong acid because it can donate a proton, just like an acid does, and force a reaction to completion. 100% strong acid. But when you look at Cl minus, it is a conjugate base. It is a base. Rithania, what is a base meant to do, Rithania? Sorry, could you repeat that?
Accept protons.
Good. Is this chloride, which is meant to be the conjugate base, is it doing its job of accepting a proton from hydronium and going the other way to reform hydrochloric acid? Is it able to cause a reverse reaction, Rithania? Yes or no? Look at the reaction direction. Is it bidirectional or unidirectional? Sorry, I can't hear you. I'm not sure. Sid, passing it on to you.
The reaction, the reverse reaction is very unlikely.
Yeah, it's technically impossible, right? HCl, strong acid, it will not go back. So what that's telling you is a Cl minus, which is meant to be a base, this conjugate base, is not able to do its job at all of taking a hydrogen or a proton from hydronium and causing a reverse reaction. If it was able to do that, this reaction would be reversible. You'd see double arrows, but we clearly don't. So the strength of this base, this chloride ion, is so negligible, it's pretty much neutral. And that's to show you that the conjugate of a strong acid is an extremely weak or neutral base, right? Does that make sense to us so far? So there are two levels here. You need to memorize the conjugate of a strong acid is a very weak / neutral base. And if you're ever stuck or unsure, you use an example and it makes a lot of sense. The conjugate base cannot drive this reverse reaction. It is so weak. But have a look here. What did we say? Sid said the conjugate of the acetic acid is the acetate ion, right? So the conjugate base that I'm going to write here, it's already been written, is this acetate ion. Now, Jacob, passing it on to you. This acetate ion is a conjugate base. In this reaction, can you see the conjugate base accepting a hydrogen and reforming the acid? Is there a reverse reaction occurring?
Yeah.
Good. So it's doing its job. Do we all agree? But is it doing its job to 100%, Jacob? Does it have 100% ionization for the reverse reaction?
No.
No. So Jacob just told us, yes, it's behaving as a base. This acetate ion is able to take a hydrogen from hydronium and force a reverse reaction. So it is definitely basic. It's not very weak, okay? But it's not strong because it can't force a unidirectional reaction one way. It doesn't have a 100% degree of ionization. So that's telling you the conjugate of a weak acid is a weak base. It's not strong because there's no 100% ionization, and it's not very weak because there is a reaction going backwards. And so that's why, everyone, we use the words conjugate acid, conjugate base. Okay? It's because they actually do behave as acids or bases, just with different strengths. Okay? So the key point here is whenever you have a strong acid or even a base, the conjugate of a strong is very weak or neutral. The conjugate of a weak is a weak. And one way I like to understand this is kind of like if this was like a HP bar or a 100% bar, a strong acid is really strong. It's ionizing pretty much to 100%. So there's very little left in this bar for the conjugate, so it's very weak. But in this case, if you have a weak acid, it takes up half this bar. The other end of the bar is about the same size, it's also weak. Okay, so think of it however you'd like to, but definitely make sure you understand it rather than memorize it. Hopefully now we understand the conjugate of a strong acid or base is very weak to the point it's neutral. The conjugate of a weak acid is a weak base, and vice versa. Any questions so far? Good. Have a look at this reaction and tell me. Okay. So here we have the bicarbonate ion. Maybe I'll show you, not bicarbonate, maybe I'll write another reaction for you. Okay. So H2CO3, H2O, forms hydronium as HCO3 minus. Okay, Rithanya, who's the acid and who's the base?
The acid is H2CO3.
Good, who's donating a proton. And who's the base then?
The water.
Good, right? Jacob, who's a conjugate acid and base? It's a conjugate acid, conjugate base.
The conjugate acid would be the hydronium, and then the conjugate base would be the HCO3.
Good. Conjugate base would be HCO3. Good. And finally, Sid, tell me the strengths of the acids and bases. So how strong is bicarbonate and why?
I'd say
Sorry, not bicarbonate, the carbonic acid. So this substance here. How strong is it?
the carbonic acid is a weak acid because it can form dynamic equilibrium.
Good.
So
Okay.
its conjugate base would also be weak.
Good. Good. And it should make sense. They're weak because neither of them can ionize to 100%. Good. And what about, so this is the case with water, it's a little bit harder, right? And with the hydronium ion, it's a bit harder. We don't describe the strength of water or the strength of the hydronium ion. The hydronium ion is an acid, and it's a strong acid, right? It's a strong acid in itself. And what's the conjugate of a strong? Very weak or neutral. Okay, now you may be thinking, doesn't make sense because if it's strong, shouldn't it be able to ionize to completion? That's why I'm saying we never ever describe the hydronium or water as a strong acid, strong base, etc. But just remember, this is a strong acid in itself, the hydronium ion. Okay, but it kind of does not operate by the rules for the rest of the substances. So we never ever describe the strength of these two substances. Good. So you'd leave it at that. Okay. Good. Any questions so far? All right. So now this is how you remember it. All of the weaknesses of Arrhenius theory are the strengths of Bronsted-Lowry theory. So if you remember Arrhenius, Bronsted-Lowry is a piece of cake. So what were the weaknesses of Arrhenius against it? What was the most important one?
Doesn't account for the solvent.
Good. And what was the reaction for the ammonia dilemma, Sid?
NH3 gaseous plus hydrogen chloride gaseous to form ammonium chloride.
Good. Ammonium chloride would be a solid because it's a salt. So it would be solid here. Okay. All right. So looking at this reaction, it makes no sense according to Arrhenius theory. There's no hydrogen ions, hydroxide ions. But Sid, how do you make sense of this according to Bronsted-Lowry theory?
So basically, ammonia donates hydrogen chloride donates a proton to ammonia. So then it forms ammonia and the chloride ion, and they
Which combine.
Yeah, combine.
Good. Actually, who's the acid and who's the base?
The hydrochloric acid is the acid and ammonia is the base.
Good, right? And don't worry about strength of acids and bases here. This is a different kind of reaction, okay? When we're talking about conjugate acid-base pairs, it's usually always in water, okay? Good. So we're not going to talk about the strengths here, but good. And I'm sure hopefully you all know ammonia is a weak base. Hydrochloric acid is a strong acid. Can anyone tell me why does it go to completion? Are there any neutralization reactions without water that don't go to completion?
What about boron trifluoride?
Okay, that's a special case because it doesn't even have hydrogen. And the reason that's one of the weaknesses of Bronsted-Lowry theory, and that's talking about amphoteric substances. So we won't delve into that because that's hard even from a university chemistry standpoint. But what I wanted you all to conclude is that all neutralization reactions go to completion, except the ones with water. Right, the ones with water, I don't really count them as neutralization, even though they technically are. See, for example, these reactions here, these reactions, that doesn't even have water, but the ones I included, like this one, it is technically a neutralization. It's a proton transfer. The reason it doesn't go to completion is because it has water. If you add any base here, if you add sodium hydroxide, even a weak base like ammonia, the reaction must go to completion. So remember that. All neutralizations go to completion. Okay? And that's if you account for neutralizations as an acid and a base, not water. Good. All right, so good job. So now we can explain acid-base reactions outside of water, as you can see here, right? What was another con of Arrhenius theory? Let's go to Akshita. Akshita, what was another con of Bronsted-Lowry theory? Sorry, Arrhenius theory. Akshita? While we're waiting for Akshita, Rithanya?
It was the salts weren't neutral.
Good, right? So that's another whole area which should not make any sense to you so far. How can a salt be acidic or basic? So this is where we're going to start talking about it. Now, before we talk about salts, we'll talk about this term called amphiprotic substances, right? Which are substances that could behave as both an acid and a base. Okay, and we'll think about how that makes sense. What does the word amphi mean? Amphi means both. It's kind of like the word ambidextrous, right? When you're ambidextrous, you're dexterous with both hands. When you're amphiprotic, right? Amphi means both. Protic refers to the proton, meaning you can both donate a proton and you can both accept a proton. Okay? Now, for you to be able to donate a proton, you must have a hydrogen in your structure. Does everyone agree? Otherwise, you can't donate the H. For you to accept a proton, you need to have some degree of negative charge. So when the proton gets accepted, it neutralizes charge. Okay? So common examples of these amphiprotic substances are HCO3 minus. Do you all see it has a H, has a negative charge? Right? H2PO4 minus has a hydrogen, has a negative charge. So now I'm going to ask you, Sid, would this be an amphiprotic substance? This one here.
Yeah.
Good. Has a hydrogen, has a negative charge. Akshita, on to you. Would this ion be amphiprotic? Yes or no?
Is my mic working now? Can you hear me?
Yep, I can. Good.
Yeah. No.
Why not?
Cause.
What were the two prerequisites? What does it need to have? A hydrogen and a negative charge. Does it have a hydrogen?
No.
Good. So it can't be amphiprotic. Does that make sense? So the main two amphiprotic substances you should know for your exams are any variation of the phosphate and the hydrogen, right? And the HCO3 minus ion. Those are your main two amphiprotic substances. Let me ask you this. Can water be amphiprotic? Yes or no? Think hard about this one. Can water be amphiprotic?
Yes.
Good, right? And that's because water doesn't really need to have a negative charge because it can gain a positive charge via or can accept a hydrogen even when it's neutral. It's one of those rare cases because remember, water can form a coordinate covalent bond, right, with a hydrogen ion and form H3O+. It's one of the rare cases where it goes from neutral to positive charge, right? So example of water, or HCl plus water would form the hydronium ion and the chloride ion. Here, water is acting as a base. It's accepting a proton. But in the same way, if I wrote NH3 plus water, well, what it's going to do now is it's going to donate a proton rather than accept a proton to form ammonium and hydroxide ions. So you can see here, water can both accept protons and it can also donate protons. Hence, it is amphiprotic. So water is another example. Very good. Now, small tip. If you're ever to write chemical reactions to confirm a substance is amphiprotic, don't do what's been done in these notes here, where you're showing the bicarbonate ion in water acting as, what is it acting as at the top? In reaction number 1, Jacob, is the bicarbonate ion acting as an acid or base? I know you can see the letters, but can you explain it to me?
Yeah, it's acting as a base. Is that just because the water's actually donating the proton?
Good, right? And in the same way, since it's donating a proton, then you could say the bicarbonate ion is accepting a proton, therefore acting as a Bronsted Lowry base. Good. What about Ruthania? Reaction 2. What is it behaving as and why?
It's an acid because it's donating its
Proton. Very good, right? Now, the reason this is not the best thing to do in an exam is because even though technically bicarbonate can do both of these things in water, all amphiprotic substances have a slight tendency to do one over the other. In the case of bicarbonate, in water, it has a tendency to behave more like a base. So if you were to measure the pH of a bicarbonate ion solution, it would be alkaline. Does anyone know where you can find 5 to 6 liters of bicarbonate ions in your home? Some of your homes would have 18 liters of it or more.
Baking soda.
No, you have 18 liters of baking soda. I'd be very surprised. I don't know what you'd be making, a bunch of cake or a cake factory. I'm talking about the human body. Your blood is a solution of bicarbonate ions. If you measure the pH of blood, it's slightly alkaline. It's 7.35 to 7.45. The number that I just said, you actually need to know for your exams, but we'll learn it later on. Okay, but small point here, amphiprotic substances have a slight tendency to act as an acid or base in water. So what you should do instead is show the amphiprotic substance reacting with a real acid, like HCl, and an amphiprotic substance acting with a real base, such as the hydroxide ion. So what I prefer to do is show, in this case, I would have shown bicarbonate reacting with hydronium and the bicarbonate reacting with the hydroxide, right? And in that case, when it's acting as an acid and donating to hydroxide, this would be water. And when it's acting as a base and it's accepting a proton from hydronium, what's left here is water as well. So this is what I would have written if an exam asked me to write 2 equations to show the amphiprotic nature of the hydrogen carbonate ion. Does that make sense? And it's because when you have a confirmed acid, it has to act as a base, the bicarbonate ion. When there is a confirmed base, it has to act as an acid. In water, it doesn't have to act as both. It actually prefers to act as a base. Any questions so far? Good, good. What I might do is see if I can give you a quick question. Question 8. Let's go to Jacob. What's your answer? When you're ready, don't rush it. Take your time, no rush. I'll give you guys about 30 seconds or
so. Is it C?
Good, right? And the reason is, like, whenever you write a base, remember, the metal ion in a base is useless. Don't worry about it. So what they're really showing you is acetate ion. CH3COOH. Sorry, CO minus. So this substance doesn't have a hydrogen you can actually donate. These hydrogens are stuck on. They're hydrocarbon hydrogens. They don't disappear. So it can't be A. Can't be aluminium oxide. That's basic, right? When you take the sodium off, it's a hydrogen carbonate ion, which we just went through. It's amphiprotic, right? Why is it not phosphate? What part of this ion makes it impossible for it to be amphiprotic? Sid?
No hydrogen ion.
Very good. Can't donate. Very good, right? Moving on. Next question. Question 1. Not too bad of a question at all. Britannia, what's your answer?
Not sure, but is it A?
Good, right? The learning point here is the conjugate acid-base pair only differ by one hydrogen. Because remember, when an acid becomes a conjugate base, it donates a proton. So it loses one H. When a base becomes a conjugate acid, it accepts one proton. It increases in one H. All the other options are changing by more than one hydrogen. So your answer is straight away A. Very good. So these are trial questions you can get, but you're never going to get a question like this in the HSC, where it's 8 marks and you have to write an essay on historical theories of acids and bases, right? So I'm going to skip that. Okay, does everyone remember the formula to calculate pH? What is pH equal to? Akshita, what's the formula for pH?
Minus log 10 H plus H.
Good. The concentration of hydrogen ions. That's it.
Yep.
Good. I want you guys to try this question. So it's just a direct calculation question. Nothing to it except at the end you'll have to find pH. So if you know the pH formula, you'll be fine for this question. So I'll give you guys try doing it in 4 minutes. If you're fast, you definitely can. At about 5:56, we'll quickly run through this question. And then I'll take you guys, then you guys can have your break. Okay. Good. All right. I'm going to get some water. I'll be right back. Okay. Anyone got an answer for this question? Sid, what's your plan of attack? What's the first step you do in these calculation questions?
I wrote the equation first.
Good. So HCl, BaOH2. Okay. And what do we make?
Barium chloride solid plus water.
Good. Is barium chloride a solid?
I think it might be aqueous. Yeah.
Aqueous, yeah. Barium chloride is aqueous. Silver, mercury, lead are the exceptions to chloride being soluble. Okay, that's for sulfate. Barium sulfate is insoluble. Good. All right, balanced. What do we do?
2 in front of HCl and
Yep.
2 in front of water.
Good. All right, so what kind of question is this, Sid? Any ideas? You've been given the C of barium hydroxide, the V of barium hydroxide, the C of hydrochloric acid, the V of hydrochloric acid. What kind of question is this?
Dilutions.
Not. Does anyone know what kind of question is it when you've been given both number of moles and you can find the number of moles of either reagent?
I think it's limiting. Is it?
Very good. Limiting excess reagent question, right? So very quickly, we've got C, we've got V. 40 times 10 to the power negative 3. C of HCl, V of HCl. 0.01 is 50 times 10 to the power negative 3. Nathaniel, what did you get for number of moles of HCl? And Jacob, what did you get for number of moles of BaOH2? What did we get? Anyone?
I got
Yep.
0.001 moles.
4? Which one?
BaOH, yeah.
0.001 moles. Yep, store it as A. And what about number of moles of HCl? What did we get?
0.0005.
0.0005. Okay. How do we fairly compare the two? What should we do, Rithania? Fairly compare one part of each reagent.
Divide by stoichiometric ratio.
Good. So you divide the HCl by 2, but we can clearly see it's much smaller already, so we don't really need to confirm that. We can simply say, therefore, your HCl is your limiting reagent. HCl is the limiting reagent. Okay, so what do we do then? Do we know any other pH formulas? I think, Jacob, you said you did a few pH questions. What are some of the pH formulas you know, Jacob?
I remember like pH plus POH is equal to 14.
Very good, right? And what is POH, Jacob? What is that equal to?
I don't really remember.
So it's the exact same as pH. So POH represents the power of hydroxide. pH is a power of hydrogen. So pH is negative log 10 of the concentration of hydronium ions, right? Same way, POH is negative log 10, the concentration of hydroxide ions. Okay, so in this question, our approach should now be, HCl is a limiting reagent. The acid is a limiting reagent. So what would you expect the final pH to be? Actually, though, should it be basic or acidic after these two substances are added?
Basic.
Basic, right? Because acid is a limiting reagent, there's excess base. It becomes basic. Okay, so what we need to actually do to find pH for this question is we need to find how much excess base we have, the number of moles of excess base, And from that, we can find the concentration of hydroxide. And from that, if we have concentration of hydroxide, what can we find? Sid?
The POH.
Good. And if we have POH, what can we find?
pH.
Very good. Right. I feel with these kinds of questions, when you actually apply these formulae, it starts to make a lot of sense. And I'll explain a little bit more about POH. There's a little bit more to qualitatively understand, but we'll do it as we go through this question. Right? Good. So now we know that our excess reagent is BaOH2. How do we find the number of moles of BaOH2 that's remaining? How do we find this? Let's go to Rithanya. Rithanya, how are you going to find the number of moles of barium hydroxide remaining? Might not work. Jacob, how would you find the number of moles of barium hydroxide remaining?
Do you just minus it from each other? So 0.001 minus 0.005.
Okay, remember, before you sub in the numbers, make sure you have a formula in place. Okay, so what I mean by that is number of moles remaining should be equal to the number of moles in total of barium hydroxide minus the number of moles of barium hydroxide that reacted. Do you agree? We've got the total, but do we definitely have the reacted amount? The number of moles of barium hydroxide that reacted should be equal to, remember the itself over other fraction, the number in front of barium hydroxide is 1 itself, the number in front of the other substance, the limiting reagent HCl is 2, and then we write the other substance HCl, right? So the number of moles of barium hydroxide actually reacted is half the number of moles of HCl, okay? That's going to be equal to half of, well, I didn't store this, say I stored this as B. It's going to be equal to B on 2. So it's actually not just a subtraction of each other, but it's going to be equal to A minus B on 2. What do we get as a number of moles of barium hydroxide that reacted? Also, small thing, if you guys are sitting at a table, feel free to stand occasionally, stretch. It's one of the helpful things of sitting in your room. You can stand, stretch, take a quick walk around the room while solving the question in your hand. I find that I can't, if I sit still for 2 hours, I fall asleep. So feel free to move and we'll get your break right after this. Sid, what did you get? What's 0.001 minus 0.0005 divided by 2?
0.00075.
Okay, good. Store it as C. That's a number of moles of barium hydroxide that's remaining. Sorry, I should not have written reacted. It should just be excess or remaining, right? Good. So what's the concentration? So now we know, okay, we've got number of moles of barium hydroxide is equal to C. What's the number of moles of hydroxide ions equal to? Rithanya, passing it on to you. Number of moles of barium hydroxide is C. What's the number of moles of hydroxide ions equal to? Think about this.
2 on 3.
So 2 on 3 C, is that what you said? Where did you get the 3? Think about it simply, right? You've got barium hydroxide, right, which is just Ba and 2 hydroxide. This is the Lego piece that is 1 block of barium hydroxide. If I gave you 1 block of barium hydroxide, how many Lego pieces of hydroxide do you have, Rithanya? 2. So the answer is, if you have X number of moles of barium hydroxide, you have 2X number of moles of hydroxide ions. So it's 2C. That's it. Does that make sense? This is very important. This exact step here, you guys have to understand really well so you don't make any silly mistakes ever. Okay? Good. Do we know the concentration of hydroxide? Can we find that out? What is the concentration of hydroxide ions? So you get an N on V. N is 2C. What's V equal to, Akshita? What would you be subbing in as V? What is the volume that this hydroxide ion is sitting in?
Is it the volume of the hydrochloric acid, so 50 ml?
Draw a diagram. Whenever volumes are being added to one another, draw a diagram, right? We've added 40 ml of barium hydroxide to 50 ml of hydrochloric acid. What's the final volume?
90.
Good. See, when you draw a diagram, how easy is it? Right, so make sure whenever volumes are being added together, you draw diagrams until you're very confident about volumes and visualizing. When I read this question, I can actually see in my head 2 clear solutions being added together in a beaker in a lab, right? You should be able to code these boring words into what's actually happening in the lab. Good. So it's 90 times 10 to the power of -3. Okay, C equals N on V. It's equal to this divided by this value. What do we get as our C? And what do we then get as POH, which is negative log 10 of hydroxide? And thus, what is pH? Remember, pH is 14 minus POH. Applying this formula here. As you can see, there's a reason this question is 4 marks long. Decently long.
Do you want just the pH?
pH and POH.
So POH, I got 1.778.
Okay, let's just pause for a moment and decode what that means. 1.78, or is it 778? Doesn't matter. 1.7, what does that mean to you in your head qualitatively? Does that mean the substance is very basic? Does it mean it's very acidic? Jacob, what does it mean to you? If you see a POH of 1.78, what is that telling you?
Well, if it was pH, it should be very acidic. Because it's POH, would it be that it's basic?
Good, very basic, right? And the way you logically infer this is, well, if POH is 1.78, then the pH is 14 minus 1.78, which is around 12 point something. A pH of 12 point something is extremely basic. And that correlates to a POH of 1.78, right? So that's how you remember. Remember, a low pH means a low pH is acidic, but a low POH is very basic. That's what I just wanted to show you as well with this question. Okay, so that's how you qualitatively understand this. Remember, the same principle applies. A change in POH of 1 unit is a change in hydroxide ion concentration tenfold. So remember that as well. So good. What's the final answer for pH, Sid?
12.22.
12.22. Good job. How many decimal places?
4.
3, 1, 2, 3, 4. 1, 2, 3, 4. Good. 4 sig figs. So you do it to technically you would be doing it to 4 decimal places in your exam answer, but we'll keep it at 12.22. But yeah, very good. Key point is pH is to the same decimal places as a lowest number of sig figs in the question, which in this case does happen to be 4. Very good. Why did they give us temperature? We never used it. Why did they give us 298, aka it's 25 degrees, I believe? Yes. Anyone? pH is temperature dependent. The pH of water is not 7 outside of 25 degrees. It's only at 25 degrees that pH of water is 7. So all of these formula that you're using, they break down outside of a pH of 25 degrees. So with a lot of pH calculation questions, they'll tell you it's always at 25 degrees. That's just telling you, please use the pH formulas that you know of. Okay? Very good. Good job. I wanted to just see how you all with calculations after the holidays and then introduce a bit of POH calculations too. All right. Before we jump back to the Bronsted-Lowry theory and pH of salts, let's put it here. Take your break. So let's recap at about 5:18. Okay. So stand up, walk around, get some food, drink a lot of water, and then I'll recap at 5:18. Okay. Any questions before we take our break? All right, good. See you guys. Okay, we're back. You hit the raise hand icon. Cool. Okay, let's go into. All right, we've already discussed amphiprotic substances. I think now we should discuss pH of salt. Sorry, I think my mic keeps turning on the iPad, so it just forced an echo for a bit. Okay, so talking about pH of salts, we can understand it best by applying this principle of conjugate acid-base pairs. So let me take you through some salts to understand this. We'll start with sodium chloride. Bethany, why is this a salt? What two components make up a salt?
An anion and a cation.
Good, right? So we draw a line between the salt to understand and break down whether it's going to be acidic or basic. The next step is we look at each ion individually. So looking at the sodium is a stable, remember this is a sodium ion. It's in a stable octet configuration. It should be 2, 8, I think 8 again, but it doesn't have any valence or has a full valence shell or no valence electrons because it's a metal. It's donated all of its electrons, right? So remember, metal ions are inert. So this metal ion will not contribute at all to acidity or basicity. Make sense so far? Good. So we've got the chloride ion now. And we need to ask ourselves, what is the chloride ion a conjugate of? Actually, what is the conjugate of the chloride ion?
Was it hydrochloric acid?
Good, right? So whenever you're answering that question, what is a conjugate of a substance? You need to ask yourself, whether I need to add a hydrogen or take off a hydrogen. You can't take a hydrogen off the chloride ion, so you need to add a hydrogen. That's it. Now, Sid, what is hydrochloric acid? Is it a strong, weak, very weak acid? Which one?
Strong acid.
Good. What is a conjugate of a strong acid, Sid?
A very weak or neutral base.
Very good, right? And so now you've come to the conclusion that the sodium ion is inert, it's neutral. The chloride ion is the conjugate of a strong acid HCl, so it is also very weakly basic or neutral. And so NaCl overall as a salt is neutral, right? And that's how you explain the neutrality of NaCl. Now, if I give you another example that actually gives you an acidity or basicity, let's pick sodium acetate. I want you all to apply the exact same principles of reasoning I just did. So remember, step 1, break it up into ions. Step number 2, look at the cation. If it's a metal, it's inert, neutral. Look at the anion, find the conjugate, and then apply the strength of conjugate acid-base pairs. When you get an answer, hit the raise hand icon. Good. Got one answer. Jacob, take it away. So what are the steps you do to find the pH of the salt?
So you separate the ions.
Good.
So yeah, and then you see if you need to add a hydrogen or remove a hydrogen.
Good. So start with the cation first. Sodium, do we have to do anything to it?
No.
Good, it's neutral. Sodium ion, all metal ions are neutral, they're inert. Good. Moving on to the acetate.
Yeah, so then we can add a hydrogen to that.
Good. And then applying conjugate acid-base pair strength. So acetic acid, is that strong or weak or very weak?
It's weak.
Good. So what would its conjugate be?
Weak.
Good. Conjugate of a weak is a weak, right? And if you're unsure, write the equation. Remember this key point. You don't need to memorize this stuff. If you're unsure, just write the equation and you'll see when you react it with water, you have a reversible reaction. And then you have the acetate ion. And you can see since it's reversible, neither one is ionizing to 100%, but they are forcing reactions both ways. They have to be weak. So good. So now you know that acetic acid is a weak acid, so its conjugate is a weak base. The anion is a weak base. The cation is neutral. What is the overall pH of this salt going to be, Jacob? Will it be greater than 7, less than 7, equal to 7?
Would it be greater than 7?
Exactly, right? Because this ion here is a weak base. Okay, so what you would say in an exam is you'd say this is a basic salt, right? And do you see how we're explaining it? We're using Bronsted-Lowry theory. We're using conjugate acid-base pair strengths to justify how ions themselves can behave as acids or bases. Okay, I'm going to give you one more example. We'll see how you guys go with this. I want you to do this one for me. I want you to do this one for me. You'll get faster the more you do. And finally, I'll give you a can you do these 3 for me? So I'll give you all about a bit more than a minute to get through all 3. When you get through them, can you hit the raise hand icon? Okay, how do we go for the first one? So, Rithania, on to you. Can you completely finish the first one? Take me through your reasoning.
Is it acidic?
Yeah, why?
Because the NH4, you could donate one, so.
Okay, all right, good. Try following the same steps, right? Just so you have a structure in your answer. So breaking it up into ions, there is NH4+. What's the conjugate of this? Conjugate of this ion. Britannia?
NH3.
Good. right? Now, are you guys starting to realize some patterns here? To find the conjugate of an anion, you add a hydrogen. Did you all see that? To find the conjugate of an anion, you add a hydrogen. Why is that? It's because anions are negatively charged, right? They're going to accept a proton to become their conjugate. So you add a hydrogen. For a cation, to find the conjugate, you take a hydrogen. So you can see cations, they're positively charged. They usually have a hydrogen if they're going to be acid or base, and they'll donate it and hence become their conjugate. Very important, because sometimes you'll come across a question where you have an ion that's amphiprotic, and then you have to think, well, there's two possible conjugates. Which one do I pick? That's where you have to remember this. Or you can use this, you can literally write another example on the side to work it out yourself again from scratch. That's easier if you just remember this, right? It makes a lot of sense. Good. So the conjugate is ammonia. Is ammonia strong, weak, acidic, or basic, Ritanya?
Is it basic?
Good, weak base. So the conjugate is a weak acid. Good. And the reason I'm telling you to do it this way is because in an exam, if you were to explain it, you can't just say the ammonium can donate a proton. That's acidic. You'd have to say the ammonium ion is the conjugate acid of the weak base ammonia, hence it is a weak acid. It can thus donate a proton, enabling pH to be less than 7. The chloride ion, on the other hand, is the conjugate of the strong acid hydrochloric acid, and hence it is neutral / very weak, and it will not contribute to the pH of solution. Thus, the overall salt is acidic. That would be an exam answer, right? So that's why I want you to follow these steps, because you can literally translate it to an exam answer, okay? But very good. Moving on to the next question, this one. Let's go to Akshita. What did you get for the second option here, this salt?
I got basic.
Sid, what did you get?
Yeah, I got a weak basic salt.
Okay, Jacob, what did you get?
I feel like it would be acidic, wouldn't it?
Britannia, what did you get?
I said basic.
Okay, so I would disagree with both answers, which is telling you something, right? It technically does fall under one category over the other, but let's break it down, right? This is your salt, split it in two. This is your cation. Sid, what do you have to do to a cation to find its conjugate base? Add a hydrogen or take it off?
Remove.
Good, so the conjugate is ammonia, which is a weak base. So what is this ion, ammonium?
Ammonium is a weak acid.
Good, so the cation is weakly acidic. Now this ion, the acetate ion's conjugate is acetic acid. That is a weak acid. What's the conjugate of a weak acid, Jacob?
Weak base.
Good, conjugate of a weak acid is a weak base. Very good. So now we have an anion that's a weak base and a cation that's a weak acid, which means you can't really say which one's stronger than the other unless you look at, pKa's and degree of ionizations, etc. So the answer is technically indeterminate. It should be neutral because a weak acid component of the salt should slightly neutralize a weak base component, but the answer is uncertain. So the answer I would have put in an exam would be the weakly acidic component may neutralize the weakly basic component, and this could still overall be a neutral salt. However, further information on degree of ionizations is required, etc. Okay, so an examiner would be looking for the answer neutral. So this is an example of a neutral salt that's actually made up of an acidic and a basic component. So keep that in mind. Last one, this option here, MgCO3. What did we get, Sid?
A basic salt.
Good, right? And I agree with that. So as Sid would have done, Mg is neutral. CO3 2- is a conjugate of HCO3-, Is this acidic, basic? Which one is it, Sid?
It's a weak acid.
HCO3 minus is a weak acid. Who remembers what HCO3 minus is? There's a word I used earlier that you should be using if you ever see HCO3 minus.
Amphiprotic.
Amphiprotic. Very good. So HCO3 minus is amphiprotic, but what did I say? It has a tendency to behave a certain way in water. What is that tendency?
Basic.
Yeah, weakly basic, right? So then you might go, oh, that means the conjugate of a weak base is a weak acid. And the answer is that's not the case. This is why I'm giving you some harder examples so you understand that the rules that we've made so far apply to the vast majority of chemicals, but there are some exceptions. And this is one such exception, because you need to think about this, right? If the bicarbonate ion here was to act as a base, what would it do? It would accept a proton. Does everyone agree? Accept a proton, bicarbonate ion act as a base, accept a proton, and form the hydroxide ions. So if this is the weak base, the conjugate weak acid is carbonic acid. But what could also happen in a very small subset of reactions, like I said, is this reaction here where the bicarbonate ion donates a proton to water and we form hydronium and this ion here. Now pay attention to this. What is bicarbonate acting as here? Is it acting as a weak base? Is it acting as a base at all? It's acting as an acid, right? So what is the conjugate base in reaction number 2? Everyone? Anyone know? What is a conjugate base?
Carbonate.
Yeah, so the conjugate base is the carbonate ion, which is telling you this ion is even more basic than bicarbonate, which we said was weakly basic, right? Now, the only reason this is way more complicated than your typical ones is because it's an amphiprotic substance, right? That's why it doesn't fall under the basic logic of the conjugate of a weak base is a weak acid, conjugate of a strong acid, a strong base is very weak. It's with this specific amphiprotic ion. The bicarbonate ion is amphiprotic, and the carbonate ion is weakly basic. So this ion here is weakly basic. Okay, good. So hopefully we understood that. Okay, carbonate is a conjugate base of a substance that's already basic in water. It has to be even more basic. Okay, this is a one-off example. I'm going to give you one other exception to the rule, and they love asking this in trial questions, which is to do with sulfuric acid. I want you all to write me the Bronsted Lowry equation for the ionization of sulfuric acid. Jacob, what should it look like? Actually, Akshita, what should the equation look like for the ionization of sulfuric acid according to Bronsted-Lowry theory? What would you write, Akshita? Quickly. Okay, while we're waiting for Akshita, Jacob?
Wait, is this where it would be reacting, or is this just like the conjugate acid and base?
So this is just ionizing in water, so plus
okay,
water.
yeah, so yeah, you'll have the hydronium,
Yeah.
And then you'll have the HSO4.
Good. Good. One thing I really liked was Jacob didn't transfer 2 protons. You should never ever do that in Bronsted-Lowry equation. It's always stepwise. So then there'd be a second reaction here where the hydrogen sulfate ion will combine with water and it will form hydrogen. We'll talk about that when jump any steps yet. Okay, but very good. Good job you did stepwise. Now, this sulfuric acid, hopefully you all know, is a strong acid, right? But the unique component is this is a Sorry guys, give me 1 second. Sorry about that. I just got a call which disrupted the headphone audio. Okay, so as I said, sulfuric acid is a strong acid, but what makes it unique is it's a strong diprotic acid. Now, in this case, it's not going to follow our rule of the conjugate of a strong acid being a very weak base. When you have a strong diprotic acid, the conjugate is a weak acid. And this is something you should all remember. So 2 exceptions to our whole conjugate acid-base pair strengths was the amphiprotic hydrogen carbonate ion, in which the carbonate is also weakly basic. In this case, the other exception is a conjugate of sulfuric acid, strong diprotic, is still a weak acid. And that's why the second equation, which is a hydrogen sulfate ion ionizing, is going to be plus water and this one will be reversible arrows to show you it's a weak acid. Okay, so right now you should pretty much understand the entirety of acid-base pair conjugate strengths and the 2 exceptions to that rule. Does anyone have any questions at all?
So all diprotic acids.
No, it wouldn't be all because this is the one example of a strong diprotic acid.
So
right?
all diprotic acids.
All strong diprotic acids, but this is the only example you'll ever come across in exams. So I would literally just say, remember sulfuric acid. Okay, Sid? Every other acid, if they give you like perchloric, etc., they'll tell you the strength. Okay, but just remember when you have a diprotic acid or even a triprotic acid, it's not going to abide by the simple conjugate of a strong is a very weak base. It will likely be the conjugate is still an acid. Does that make sense, Sid? Because it already has so many hydrogen ions, it can still keep donating if it's triprotic or diprotic. Does that make sense?
Yeah, and amphiprotic substances, like, they tend to act as weak bases.
No, only the HCO3 minus ion. Not all amphiprotic substances, but they all have a tendency. You just don't need to memorize that. Okay. You don't need to memorize bicarbonate slightly basic but amphiprotic. Just say it's amphiprotic in an exam, you'll get full marks.
Yeah.
Okay. Good. Any other questions? Anyone? Good. All right, so right now you understand pH of salts, you understand conjugate acid-base pairs, you understand strengths. We now need to talk about the limitations of Bronsted-Lowry theory. You can have a look at all the other strengths that he explains. As you can see here, this is Bronsted-Lowry theory explaining how carbonates can act as a base, right? You have a carbonate in water. Well, what does a base do, Ruthania? What's the definition of a Bronsted-Lowry base?
A proton acceptor.
Good, so you can see it accepting a proton. to form the hydrogen carbonate ion and then releasing hydroxide ions. So now we understand how compounds that don't even have hydroxide in their structure can interact with the solvent and release that hydroxide, right? So pretty much every single error of Kahn of Arrhenius theory is explained by Bronsted-Lowry theory. Now, Bronsted-Lowry theory has technically two cons, but one main con you need to mention, which is the point about amphoteric substances. Later in chemistry, we found that there are compounds that don't even have a proton that can act as an acid. They can't be proton donors, but they're still behaving as an acid. And the way we know they're behaving acidically is we measure the pH is less than 7, right? And you can see an example here, boron trioxide, right? Engages in reactions in water, eventually release hydrogen ions. Lucky, you don't need to memorize any of this examples or reactions. I just like to remember this substance here, and I'll tell you why. Okay, so there are certain substances that don't have hydrogen that can behave acidically, and there are certain substances, right, that don't have hydrogen that can behave as both an acid and a base, right? And those substances are called amphoteric. Okay, so you might be wondering, this sounds a lot like amphiprotic. What is the relationship? The relationship is the umbrella term is amphoteric. Any substance that can behave as an acid and a base is termed amphoteric. If it has a hydrogen or a proton, the answer is yes, it is called amphiprotic. Okay, so the key weakness to Bronsted-Lowry theory is could not explain the behavior of amphoteric substances, substances that can behave as an acid and a base, but they don't have a proton to donate. Okay, and the second con is that there is a newer theory of acids and bases that you likely don't need to know well for the HSC, but it explains that the behavior of acids and bases is not about the proton, actually. We're looking at the wrong level of scale. It actually has to do with electrons and electron pairs. Let me explain that point. So as you'll remember, when we have an acid, it releases a hydrogen ion, and that hydrogen ion is not stable. So what it aims to do is it tries to form a coordinate covalent bond with water to become H3O+. Okay? What this new theory called Lewis theory of acids and bases, it's quite old actually, we just don't use it until maybe you get to university and you do chemistry. What Lewis theory states is that an acid is not a donor, it's an acceptor. And it's not of protons, but of electron pairs. So an acid is now not a proton donor, but an electron pair acceptor. And it says a base, right? What was a base? A base was a proton acceptor, and base is now a donor. And it's not a proton, it's electron pairs. So let's try understanding it in this little thought experiment, right? Where we have this hydrogen ion trying to attach to water to form hydronium. What is a hydrogen doing, everyone? Is it donating a pair of electrons to that oxygen in the water, or is it going to that oxygen and is it trying to take that electron pair or accept that electron pair from oxygen? What is the hydrogen doing in this example? Britannia? What is hydrogen doing? Hydrogen has no electrons. So is it donating an electron pair, or is it going and forming a coordinate covalent bond where it's accepting both those electron pairs of water, Britannia?
It's donating.
It's not donating because hydrogen ions have no electrons. Think about it. Hydrogen atom has 2 electrons. When it's an ion, it has no electrons. So it's not donating any electrons. What the hydrogen is doing, think about what is water's structure? Water is oxygen with 2 lone pairs connected to 2 hydrogens, right? So when this hydrogen is being released from an acid, the hydrogen is going to the water molecule. It sees this free electron pair in the water molecule and it goes and accepts it. It takes it and it forms a coordinate covalent bond. A bond which is covalent, but both the electrons are coming from one molecule and not being shared evenly. Okay, so in this case again, Jacob, what is hydrogen behaving as? An electron pair donor or acceptor?
Acceptor.
Good. So since it's behaving as an electron pair acceptor, would you call this a Lewis acid or a Lewis base?
Acid.
Good. So it is now what we call a Lewis acid, right? And who's the Lewis base? Who is donating an electron pair, Sid, to this hydrogen ion?
The water molecule.
Good. So the water molecule is donating it. So we call it the electron pair donor. So it is the Lewis base. Now, you will never be given questions about Lewis acids and bases. Very, very low yield. So even if you don't really understand this, hopefully you do understand this, but even if in 6 months you forget this and you just remember the definitions, you'll be fine for your exams. So just know there is a newer theory, and that's one of the cons of Bronsted Lowry theory. It's actually not about the protons, it's about electrons. Do you realize it's a question of scale? What we did now was we zoomed in from the proton. We said, wait a minute, let's actually zoom in and look at what's happening with the electrons and define acids that way. And that worked out better because now we can start defining acids and bases without even looking at the proton. Any questions? Good. Remember, this is low yield. Just remember, con of Bronsted-Lowry theory is not about protons, but electrons and amphoteric substances, and you'll be fine for your exams. Good. Any other questions about Bronsted-Lowry theory? So you should now understand the definition of Bronsted-Lowry theory, all the pros, which are the cons of Arrhenius, and then 1 to 2 cons of Bronsted-Lowry theory. You should understand conjugate acid-base pairs strengths and pHs of salts. Any questions pertaining to those concepts? Okay, good. So now we're on to inquiry question 2. Now, parts of inquiry question 2, I'm going to more or less skip because there are parts or dot points here which you can literally read in your own time. I'll just tell you what you'll need to know. For example, the first dot point, conduct a practical investigation to measure pH of acids and bases. All right, so can you guys hit the raise hand icon? Have you done the red cabbage practical experiment at school? Yeah, good. So this is literally where you get red cabbage, which has this active ingredient called anthocyanin. It's like a purplish dye. And that anthocyanin is an indicator. So you boil the cabbage until the pigment is in the beaker. Let me see if I've got an image. Yeah. You boil the cabbage until the pigment is in the beaker, and then you'll decant it or pour it to another beaker, preventing the cabbage leaves from transferring across. And then you've got a purple solution. And then you pipette little bits of this purple solution into acids and bases, and you've got an indicator which is measuring pH. So for this, all I'd want you to do is have a read of the red cabbage practical experiment in your own time, or just have a note of the words I use, such as decant, the equipment, tripod, indicator, pasture pipette, and you'll be fine. Sometimes Charles will ask you to write the method. That's the max detail you need to know this too. Any questions about 2.1? I brushed through it because it's very low yield, not important. As long as you remember the active ingredient and some scientific terminology, you'll be fine. Okay, let's actually answer the inquiry question. What is the role of water in acids and bases? What are you guys going to say? What is the role of water in acids and bases? Sid, how would you answer that question if your friend asked you, what is the role of water in acids and bases?
it determines which direction the reaction will go. So if it will act as an acid or a base.
Okay, so it influences the acidity and basicity of the solutions. Good, but can anyone tell me in a bit more detail? Maybe to do with protons, to do with actual neutralization.
Does it allow to dissociate?
Okay, yeah, that's a short answer. Do you want to flesh that out a bit more, Danielle?
It like dissociates by transferring like hydrogen ions, right?
Is it just hydrogen ions that water will transfer?
Or OH ions.
Good, right? So in summary, what you've all said to me, I'm just compiling what you said, was water enables other substances to act as either an acid or a base, as it can be accepting protons from other substances, which allow them to act as an acid, and it can act as a source that donates protons, that thus enables other substances to act as a base, right? So water is kind of like a medium that contains a proton and also has space to take protons and accept them to allow other substances to be acidic or basic. So that's how you'd broadly answer that inquiry question. Okay, good. Any questions about inquiry question 2? Good, good. All right, so that leads us to our pH calculation questions. We don't have enough time to go through this in depth at all, so maybe we'll stop the lesson there. What I want you to do next lesson, or before next lesson, is make sure you have a deep look at 2.2 and you do some of the questions, especially the pKa, Ka questions. This stuff is very high yield. I would say in Mod 6, the highest yield concepts would be titration, and shortly behind titration, this stuff. Everything else is quite easy, quite low yield. pH, Ka questions you must master. Titration you must understand very well. You can do that Mod 6 as a breeze. So make sure you have a read of it. Make sure you do as many questions as you can, so when you come into class next week, you're confident we can go through it faster. Okay? Does anyone have any questions before we finish up today? Good. A small note, make sure you guys fill in the Google Forms for the booklets if you want that posted and sent. I'll only have time to print, bind, and post everything at once. So if you're late, I might not be able to get your booklet binded, printed, and posted in time. So I'll be doing that likely on Monday or Tuesday. So make sure you fill that Google form as soon as you can, so I can get it sent to you. Cool. All right, guys, I will see you next week. Ruth, any question?
I think I sent you a message of the thing.
Yes, I got your message regarding the booklets and stuff. I'll get that sent to you.
Okay, and also it's just about school.
Yep.
Our teacher is doing something called flipped learning. I don't know if you're aware of that.
Maybe okay. We'll talk about this after, because after the class. So just stay back with Danielle. We'll discuss what your teachers are doing. All right. Have a good week, guys. I'll see you next Saturday.
Bye. Thank you.
Bye, Akshita. Bye.
Yeah, thank you.
See you, Sid. See you, Jacob. Have a good week. Just Daniel, what is flip? Let me stop the recording first. Yeah, what is this flip learning that